पल पल दिल है हमर तुम कहते जिस जगह गई चाहते अब मेरे छीन लूंगा तुम्हें सारे धोने से तेरे इश्क है एक मेरा इश्क है कह दिया है ये मैंने बोले ना नहीं बंद खोलने जिस रास्ते तो ना मिली उस पे नहीं मेरे कदम किसी जिस जगह you are comparing the current event to the destination against the current distance to the destination. Oh, ho, ho. Okay, okay. जिस जगह चाहते छीन तुम्हें सारे दुनिया से on the internet is defined as the minimum distance among all unvisited nodes. Line 15. Next version list collects all the unlisted nodes that have exactly entry distance. Therefore, next field is never be empty. Move the summation and energy to the value of the function outside of it.
in order M time.
कर दे बंद. वही ले जाऊं दिल से देखा हजारों दफा फिर बेकरारी कैसी है संभाले समझता नहीं कुछ बात आप में थी लेके इजाजत बस आपसे सांसें ये की जाती है संभाले समझता नहीं हर में दूरी साथ से कुछ मेरे बेताब कैसे तुम मिले हो कैसे तुम मिले कैसे मिल रही हो फिक्र से हो भाग भाग टिके चल 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 भर मिचुरी सोहिया सिंह बेताबियां ये कुछ और बेताबियां ये दिल का दरिया जिस रासत में तू ना काहे नहीं सॉल्व करे रे बाबा. 0 से 1 मेरा है. सॉरी 0 से 1 है मेरा 10. 0 से 2 है 50. 0 से 3 है 300. Now 5 and 6 है तेरा 45. And 2 to 1. 1 30. 64. 64 is like 37. 1 to 6. 65. 2 to 5. 2 to 5 is 76. 76. 1 to 3. 1 to 3 is 40. And 3 to 4 is 60. And 2 to 4 is 120. 2 to 4 is 20. Okay, okay, okay. So first of all 0 मार्क किया, ये 0 हो गया. तेरा 10 ये बर्न हो गया 10 में. और ओके 10 10 बर्न हुआ तो ये हो जाएगा 70. ये 50 हो जाएगा 75. 250 में बर्न होगा. 250 में बर्न होगा तो हो गया टोटल 0 0 1 तेरा 10 में 240 में 3 तेरा 50 में होगा. और तेरा 70 में 5 होगा लाइक 145 में. एंड 6 होगा 75.
So we are looking at minimum cost spanning trees, and we said that there are two broad strategies. Growing it, we will, one of them is called Prim's algorithm, right? So in Prim's algorithm, we will try to find a minimum cost spanning tree by incrementally growing it from a small edge. So in particular, we could start with the smallest edge, right? And then we will extend the tree by adding the smallest edge from the tree. So we already have a tree in Prim's algorithm. So starting with one edge, so one edge is a tree, right? So we will start with something that's already a tree, and we'll see in what way we can grow this graph within the graph that we're looking at. What way we can extend this tree while keeping it a tree in a minimal way, right? So we want to add the smallest edge to the existing tree to get a larger tree until we can grow no more. So that is broadly Prim's algorithm, right? So here is Prim's algorithm at work. So I first start with the smallest edge. In this case, the smallest edge weight is 6. So I start with edge 1, 3. Now I have to grow this tree, right? So I can either add this edge, or I can add this edge, or I can add this edge, or I can add this edge. Because I cannot add edge 8, because if I add the edge 8, then I would have essentially, if I add the edge 8, then I would have two disconnected components. I would have 2, 4, and 1, 3, right? So I cannot add the edge 8. So I would add, among the others, the smallest edge to extend the tree. So for instance, I would pick the edge 10, because 10 is the smallest of these. So now I have this. Now, among those which are connected, the smallest is 18. But if I add 18, then is the 4 and 1, 8, essentially not add edge 8, because if I add, or I can add this edge, or I can add 6. So I start with the edge 1, 3. Now I have to grow this tree, right? So I can either add this edge, or I can add this edge, or I can add this edge, or I can add this edge, because I cannot add edge 8, because if I add the edge 8, then I would have essentially, if I add the edge 8, then I would have two disconnected components. I would have 2, 4, and 1, 3, right? So I cannot add the edge 8. So I would add, among the others, the smallest edge to extend the tree. So for instance, I would pick the edge 10, because 10 is the smallest of these. So now I have this. Now, among those which are connected, the smallest is 18. But if I add 18, I will end up creating a cycle. So this adding 18 will not allow me to keep this a tree. So the smallest edge I can add which keeps it a tree is, so I cannot add that edge. So the smallest edge I can add to keep it a tree is 20, right? And finally, now I have reached the point where I can add the edge 8, so I can add that, and now I get the spanning tree. So this is Prim's algorithm. I start with the smallest edge 6, take the smallest edge which is connected to the current tree 10, smallest edge is connected but doesn't form a cycle, that's 20. And then 8, and then I get a spanning tree, right? So we have to argue that this is correct, of course, but this is Prim's algorithm. Right? So Prim's algorithm says incrementally build a spanning tree, so both of which are parts of the existing graph. So initially I have nothing, right? So any edge, so this is okay. So what do we know? We know that this is the small other path. Which Prim's algorithm, remember, is that at every point we have constructed, what we're doing is we are trying to than that, consisting of one point. This be okay. Initialize distance to infinity, right? We initialize visited to false. Actually, as usual, we define infinity. So we are directly working with a list because we know that it cannot be worse than working with a matrix. So we work with a list, right? Smallest edge Prim's algorithm anywhere in the graph, this must be the smallest edge connecting I to the rest. You will get a correct answer because that will be still by the minimum separator lemma part of every spanning tree. We're going to keep track of the tree that we have built. Okay? And we're going to keep track of the distance of every vertex. Remember that we have to take the shortest distance for every vertex from the tree that we have built and pick the vertex which is the shortest distance. And we are going to keep track of the tree edges. So remember, so this is basically going to tell us what we call TV, right? This is going to tell us what we call TE. And this is going, distance V is going to tell us the distance from every vertex to TV. That is the smallest edge connecting, right? And this is going to tell us what we call TE. And this is going, distance V is going to tell us the distance from every vertex to TV. That is the smallest edge connecting V to the tree, and we are going to pick the minimum among those at every step, right? So these are the three things that we are going to keep track of. So initially, as usual, we define infinity. So we are directly working with a list because we know that it cannot be worse than working with a matrix. So we work with a list, right? So we initialize visited to be a dictionary, distance to be a dictionary, and tree edges to be a list. Right? So empty dictionary, empty list. Now the first thing what we do is that for every vertex we initialize visited to false, and we initialize distance to infinity. Right? So initially there is no tree. So every vertex is unvisited, and every vertex is infinitely far from the tree because there is no vertex in the tree. Now we set some vertex to be in the tree. So we said before that it is not necessary to start with the minimum vertex. So we can just pick vertex 0 and say start the tree at 0. Right? So eventually in the tree 0 has to be there, and we said that the smallest edge connected to 0 will actually form part of it. So once we have thrown 0 into the tree, then 0 is part of TV. So if I have 0 there, right, vertex 0, and if I look at all its neighbors, they are now connected to the tree by edges to 0, and that now defines their minimum distance to the tree. Right? So for every vertex in the adjacency list of 0, I set the distance to that vertex to be the distance of that edge, the weight of that edge, right? So if I have u 0 to b with distance d, it will be a pair v comma d in the adjacency list of 0. So I will set the distance of v to be d. So this is my initialization. So I have set up a trivial tree with one vertex, and I have initialized the distance of all its neighbors to be the distance of the edge from 0 to its neighbor, right? And now I do the usual thing, which is I will try to calculate the minimum distance, right? So I initialize to, I will do the traditional minimum distance thing. I will set minimum distance to be infinity, and then I will find it, right? And I will set the next vertex that I want to add to be none, right? So essentially I will go through all the vertices, right? And I will check whether it is visited, and if its minimum distance, right, is currently smaller than the minimum distance of the, so this is, right, so basically I take an edge u comma v, I check that u is visited, v is not visited, and this is the distance, right? And I check whether this distance is actually smaller than the minimum distance that I am trying to calculate, and if so, I update it. So at the end of this loop, I have found the distance which is minimum, and I have found the next vertex, and I found the next edge also, which is the uv. This is the next edge to be added, right? So if I have not found a vertex to add, I come out of it. So this will be a paradox, this will be a pathological case when the graph is not connected, which we need not worry about, but I put it for completeness. But in general, I will come to this point, right, where we have now identified this minimum vertex, right? So we've identified this minimum vertex, and now we set it to be true. We append the edge that we have discovered from u to v, so there's a bracket there, u to v to be there, right? And now for every neighbor of the vertex that we have just discovered, for every v comma d which is in the list of next v, if it is not visited, we update its distance, right? So this is how Prim's algorithm works. But if we look at the complexity of this algorithm, okay, the initialization takes order n, the loop runs n times as usual, okay, and now in this loop we have this which is actually looking at all the edges, right? So it's saying for every edge, if the starting point is inside and the ending point is outside, then consider the distance and add it, right? So this is terrible because this thing is actually n times n, right, which could be n cubed, and we would hope that this would be no worse than n squared, right, similar to say Dijkstra's algorithm. So we have to do something a little more clever to get this algorithm to actually come down to a reasonable complexity. So we will do the same thing, but we will maintain our information a little differently, right? So as before, we were clever to get this algorithm to actually come down to a reasonable complexity, right, outside, okay, and now in this loop we have this which is as usual, takes order n, the loop runs n times as usual, okay, and now in this loop we have this which is actually looking at all the edges, right? So it's saying for every edge, if the starting point is inside and the ending point is outside, then consider the distance and add it, right? So this is terrible because this thing is actually n times n, right, which could be n cubed, and we would hope that this would be no worse than n squared, right, similar to say Dijkstra's algorithm. So we have to do something a little more clever to get this algorithm to actually come down to a reasonable complexity. So we will do the same thing, but we will maintain our information a little differently, right? So as before, we will keep this visited and this distance, but remember that every time we update the distance, we have a reason to update it, right? So we updated the distance because we discovered the distance from the most recently added vertex was smaller than the distance we had before, and therefore this edge represents the edge which connects this unvisited vertex to the tree in the smallest way, right? So supposing I had this thing and I had a vertex v there, and now I grow my tree to this point, and now I discover that this distance is smaller than whatever distance I had from here to here. So I throw away that and I say that this is my new distance, but I also know that this edge is the reason why this vertex has this distance, right? So when I compute the minimum distance, I will also recognize which edge I added. So I will keep track of this neighbor, right? So distance v tells me how far away v is from the tree, but neighbor v tells me which vertex in the tree is actually connected at that distance. So remember that this is not the shortest path distance, this is a direct distance. This is an edge connecting v to the tree, right? So where is the other endpoint of the edge? That is at neighbor of v. Right? So now this becomes my new thing. I no longer need the tree edges because I will discover them from the neighbors. Eventually the neighbors will form the tree, right? So what I will do is, instead of keeping the tree edges, I will keep the neighbor, right? And initially the neighbor is also a dictionary which is empty. Now I initialize visited to false as before, distance to infinity as before, and the neighbor of every vertex I initialize to -1. -1, it should be a name of a vertex between 0 and n minus 1. So since it's -1, it's not defined, right? Now as before, I start by setting visited of 0 to be true. And Now I do do two things. Used, right? And initially this set of tree edges is empty, so we don't have a tree to begin with. Now we scan the edges from the first to the last, from 0 to n minus 1, and we try to add it to the tree, right? So if we try to add it to the set of tree edges, either it will create a new component by combining two components, or it will try to connect two parts that are already in the same component. So if it is going to create a loop, we skip it, loop or a cycle, otherwise we add it, right? So let's look at a more complicated graph. It's a little easier to visualize. So here are all these edges. Now we sort them, right? So when we sort them, we find that this is the smallest one because it has weight 5. Then this is the next smallest one because it has weight 6. Then now easier to visualize. So here are all these edges. Now we sort them, right? So when we sort them, we find that this is the smallest one because it has weight 5. Then this is the next smallest one because it has weight 6. Then we have 3 at weight 10, right? So we have these 3 edges all at weight 10. So we put them in some order. So say 0, 1, 4, 5, and 4, 6. So we are ordering them by the vertex number. Then we have this 18 weight edge, which is 0, 2, right? And then finally we have this 20 and then the 70, right? So this is the order of edges that we are going to process in ascending order of weight. So initially our tree is empty. So we overlook order of from 0 to m minus 1, and we try to add it to the tree, right? So if we try to add it to the set of tree edges, either it will create a new component by combining two components, or it will try to connect two parts that are already in the same component. So if it is going to create a loop, we skip it, loop or a cycle, otherwise we add it. Right? So let's look at a more complicated graph. It's a little easier to visualize. So here are all these edges. Now we sort them, right? So when we sort them, we find that this is the smallest one because it has weight 5. Then this is the next smallest one because it has weight 6. Then we have 3 at weight 10, right? So we have these 3 edges all at weight 10. So we put them in some order. So say 0, 1, 4, 5, and 4, 6. So we are ordering them by the vertex number. Then we have this 18 weight edge, which is 0, 2, right? And then finally we have this 20 and then the 70, right? So this is the order of edges that we are going to process in ascending order of weight. So initially our tree is empty. So we can always add the smallest edge. So this is what we saw with Prim's algorithm also, that we could always start with the smallest edge, or we could start there with any vertex and pick its smallest neighboring edge. So here we can always start with the smallest edge because, right, to begin with, everything is an isolated component. So the first edge will merely merge two vertices into a single component with two vertices. So after I do this, now I go to the next smallest edge, which is this one, right? and notice that this is going to create another component far away which has no problem, so we add that. Now we look at 0, 1, so that's this one, right? So when we add 0, 1, again it doesn't create any problem, so we add it. Now we look at 4, 5, this is our next one. So 4, 5 is going to be this edge, so again we can add it without a problem. Now we look at 1, 4, sorry, we look at 4, 6, right? Now if you look at 4, 6, the problem is that we already have these two edges, right? So 4, 6, if we add, it's going to create a cycle, so we have to skip it. So we skip over 4, 6, doing nothing, right? And now we look at the next one, which is going to be 0, 2, because we move from 10, the next smallest in the ascending order, the next is 18. Again, we have a problem because we've already added these two edges, so we cannot add that edge. So we will have to skip 0, 2 as well. Okay? So we have skipped these two edges, 4, 6 and 0, 2. Now we find 1, 4 is our next possible edge, and adding that doesn't create a cycle, so we add it. And finally, we have only one edge left, which is this 2, 3, the largest edge, but that's the only edge which connects to 3, so eventually it makes sense, it has to be in the spanning tree, so we add it and we're done. Right? So this is how Kruskal's algorithm works. So the correctness of Kruskal's algorithm follows from the same observation that we use to justify Prim's algorithm. And of course, we have some we add it to each other, the sort must be there in the spanning tree. Right? So we are using essentially the same formal argument as Prim's algorithm to justify that every time Kruskal's algorithm adds an edge to the tree, that edge is a valid edge to be added. So the implementation of Kruskal's algorithm is reasonably straightforward. So what we have to keep track of are the edges in my tree. So that is this tree edges, right? And we have to now keep track of two things. We have to keep track of the vertices and the edges in sorted order to process, and we have to keep track of these components. So this is something which is new compared to the other things, because we didn't have to keep these, which group of vertices are connected to each other in any of our earlier algorithms. So the first thing we do is we sort the edges. So what we do is we take the edges are of the form typically u comma v comma distance or weight. So what we will do is we will represent them instead as d comma u comma v. So we put the weight in the front because we want to sort by the weight, right? So we create this list of edges by putting in d comma u comma v for every edge v comma d in the list associated with u. So we process so we create this list of edges by putting in d comma u comma v for every edge v comma d in the list associated with u. So we process the adjacency list starting vertex by starting vertex, and for every vertex in that list we just throw it in, right? Now having done this, we sort this, right? And of course this was just something which I had used to. check my code. So we sort this and now we have the list of vertices in ascending order, right? Now we just process them in that order. So we take this d comma u comma v in this edge list, right? And we check whether the component of u is the same as the component of v. Now initially we said that every component must be a singleton. So that we have done in this list. So whenever while we are processing the adjacency list, right, we are also assigning to every component, every vertex, it's a name, right? So we are creating n components 0 to n minus 1 by saying component I is I, right? So the vertex 0 belongs to component 0, the vertex, so we are naming these components. So the initial names are 0 to n minus 1, right? So each vertex belongs to a component whose name is the same as the vertex. Now what happens when I merge two vertices, right? So I have a vertex u and I have a vertex v, and these belong to some component, right? So this component over time has some name. So this is some I and this is some j, right? Because originally the components which belong to vertex I and vertex j, and as we merged, we have to, so when we merge two components, we keep one of the name of one of them, right? So if component 1 merges with component 7, then we get a new component. Now we call that new component either 1 or 7, right? It doesn't matter, but we don't have to create a new name for it. So either we rename all the ones which were called 1 as 7 or all the 7s as 1. So that's basically what's happening here. So what we do is we remember the name of the component that we are at one endpoint of the edge, and for every other vertex which has that same component, we change its component to the other point. So basically everything from here is now going to get called j instead of I, right? So this is going to extend this component. So when I take two components and I merge them, if this is component I and this is component j, either I make everything in I and call it j, or I make everything in j and call it I. So what I'm saying here is if the edge is going from I to j, I'm going to convert everything in I to j. So that's what this loop is doing, right? So it's saying that let C be the component of the starting vertex, and for every other vertex which has the same component name, change it to be that of the target vertex. The reason that we have to save this name is because once we process u, that name will change. So that if there are vertices after u which have the same component as u, then I will not know what their component should be. So that's why I keep a copy of this small c to remember the component name of u before I change it, because in the process of changing it, u may change before some of the other vertices in that. This name is because once we process u, that name will change. So that if there are vertices after u which have the same component as u, then I will not know what their component should be. So that's why I keep a copy this small c to remember the component name of u before I changed it, because in the process of changing it, u may change before some of the other vertices in that component, right? So this is a very straightforward thing now. Basically we process, initially we sort the edges by weight, right? We assign the component of each vertex to be itself, and we have an empty set of three edges, and whenever we find an edge which spans two components, we add it to the tree, right? And we relabel the components associated with it. Now technically if you look at this initialization, right? So one thing you will see is that if I have an undirected graph, if I have uvd, I will also have vu. So technically every edge is going to come twice in this list of edges. But remember, the first time I add an edge, it will merge the component. So if I see it again, it will just ignore it. So it's not a real problem if I keep the edges in both directions in an undirected graph in the sorted list, because the first time it will get processed in whichever direction I pick it up, and when it comes in the reverse direction, I will just ignore it, right? So this is how the algorithm works. So the main problem with this algorithm is really this loop, right? The problem is that I need to, every time I merge two components, I need to scan through all the vertices to decide which one's components change, right? So we have to merge all these vertices. There's no way to avoid this, because although we know that u is joining v, we don't know which other vertices are also connected to u. So we have to go through and explicitly make all of those vertices which are connected to u also connect to v, right? So the first step, which is sorting the edges, right, we know can be done in m log n time if you use an efficient sorting algorithm. Now it is a simple thing to observe that because m is at most n squared, right, log m is at most log of n squared. But if you know how logs work, this is the same as 2 times log of n. So this is big O of log of n, right? So log of m and log of n are really the same. When I take logs, the fact that m is n squared doesn't matter. So I can also write m log m as m log n. It doesn't really matter. And the reason it's useful to write m log n is because later on we will see that some of the complexity depends on n and not m. So sorting is m log m, which we can also think of as m log n if we wish, right? Now this outer loop runs m times, right? For every edge in my sorted list, I have to do something. But I do something only when the edge is going to contribute to the tree, right? So I actually do this part only n times or n minus 1 times, because the tree on my n vertices is going to have n minus 1 edges, right? So most of the times this if condition is going to say the component of u is equal to the component v, and I'm going to just skip over to the next edge. The only time I have to do some work on the edge is when it is actually a tree edge, and that happens n minus 1 times. But what I have to do in those n minus 1 times is to update all the components potentially which are there. It could be one, it could be a lot, but I have to scan all the vertices, and wherever I see a vertex whose component is the one getting merged, I have to update it, right. So this is an order n scan. So n into n minus 1 says inside this loop, even though the loop happens m times, right, there is actually an n squared amount of work being done, because n minus 1 times I am doing a scan of n vertices, right. So this gives us an overall complexity of n squared, right. Now n squared is not something that we would like, but this is the same problem that we faced. It's a different problem in the sense that this is not due to the data structure that we were facing with Prim's algorithm and with Dijkstra's algorithm. So there we were getting an n squared factor because every time we had to scan all the vertices to find the minimum one to be added next. And we did not have a clever way to extract the minimum if the vertices are not in any particular sorted order. Here the problem is different. Here our problem is that when we update a component, we have to scan all the component names and update all the ones which have the same component as the one that is being merged. And we have no clever way of understanding which ones need to be merged now. So the bottleneck is really in this naive strategy to label and merge components, right. So remember that these components actually represent a partition of the vertices. So a partition of a set is if I take the set and I actually break it up into disjoint subsets such that the sum of all the subsets, the union of all the subsets is the whole set, and no two sets in that partition will intersect with each other. So we have a collection of disjoint sets. So what we really need is some way of maintaining this collection and performing some operations on these. So what are the operations that we need? Given one element of the whole set,